Hello everyone, I am Kailash Prasad, a PhD scholar at Nanoelectronics Devices and Circuit Lab, IIT Gandhinagar. Today I'm here to for live session 7, and this live session has already happened in the last week. I'm re-recording the live session because the recording has failed in the last one. If you have some doubts or questions regarding this, you can write back to me in my email address, or you can ask in the discussion forum in the NPTEL, or you can ask in the Hangout group or the WhatsApp group which we have created. Okay, let us start. As of now, what we have done in the entire course is we have been discussing about VLSI design and the basics of the VLSI design. And in the week one, we have started with CMOS transistors and current model. Then we have discussed about the CMOS inverter and the characteristics. Then we followed it up with noise margin and delay of inverter, followed by RC delay. Further, we have also understood that okay, how to optimize the delay. We have discussed about the Elmore delay and all. Further, we have designed many of the combinational circuits. We have seen various kind of combinational circuits which are available, right? And we have also understood what are the advantages and disadvantages of all the individual combinational circuit. Then moving to the next part, we have discussed the layouts and the stick diagrams, and we have discussed in a greater detail the interconnects in the week 7 and week 8. Last lecture was about week 9 in the power and the static power interconnects, and then the static power. I'll be discussing about week 8 and week 9 in this part. Let us start with the very first question. Okay, so the question here says that the wire with a total length L is partitioned into n identical segments, each with a length of L by n. Then the resistance and capacitance of each of the segment are hence given by R L by n and C L by n. Okay, and with R is equal to RL and C equal to CL, right? So this is the question, and the total lump. So this R and C, the capital R and C, are the total lumped capacitance. Okay, and the individual capacitance is what? R L by N and C L by N. So the question is using L model and the L model formula, calculate the time delay of the wire. So that's the question we have. The very first thing what we have to do is we have to make the RC network using the L model and the L model delay model, right? So let me quickly make the model for you. So the model will look like something like this because we are following the L model. Okay, so R and C, then again R, then C, and this will be followed by the last R, okay, and then C. This will be the Elmore delay model, and what will be the individual capacitances, right? So this will be C1, C2, C3 to Cn, then R1, R2, R3 to Rn. Okay, in the question what it has mentioned that all the individual components of this, or all the individual resistance and capacitance are equal, and how much it is? RL by n and CL by n, right? So R1 and C1, so R1 is equal to R2 is equal to Rn is equal to RL by n, and then C1 is equal to C2, then is equal to Cn, then RC by n, right? Please note that okay, not CL by N, not R, yeah, CL by N. Okay, so please note that capital R and capital C uh, are the lumped capacitance, where individual R and C are the individual capacitances. Okay, so now what we have to do, now we have this network, we just have to apply the Elmore delay formula. So if I directly apply the Elmore delay formula, the time will be, time tau will be, so R1 that will be multiplied by C1, then R1 plus R2 will be multiplied by C2, then it will be like this, and then Rn will be R1 plus R2 up to Rn will be multiplied by Cn. So this is the equation which will be coming if we apply the Elmore delay model. And now what we have to do, we just have to simply put the value of R1 and C1, right? the R1 is RL by N. Okay, C1 is CL by N. Similarly, here again RL by N plus CL by N. Okay, no, RL by N twice plus multiplied by CL by N. Okay, and this will be followed here. It will be RL by N plus RL by N, right? And it will be multiplied by CL by N, right? So now if you simplify this equation, as you can see here that L by N square can be taken out and RC can also be taken out. So here it will be RC L by N square, okay? And this will be 1, then here it will be 2, then here it will be 3, and it will be like this, right, till N. Okay, now if we simplify it again, and it's an arithmetic progression, so you apply RC L by N square, okay, multiplied by n plus 1 by 2, that is the sum of n numbers, and n plus 1 by 2. Okay, so if we simplify this, 1 n will be cancelled from here, and it will be, it just, you need to see how I am writing is R multiplied by capital L, C multiplied by capital L, okay, and then it is actually multiplied by n plus 1 divided by twice n, okay. And now this R multiplied by L and C multiplied by L, as we have seen over here, that this is nothing but the total lumped capacitance and resistance, right? So the final answer will be capital R multiplied by capital C. This will be multiplied by n plus 1, then divided by twice n. Okay, so this will be the final answer. So in this option, if you can see, there will be this option, I guess. Yeah, that is the first one, RC multiplied by n plus 1 divided by twice n. Okay, so this is how we have to approach this question. Okay, in the question we had been mentioned that, okay, there was a wire which was divided into n fractions, and individual resistance and capacitance was given, and the second part that was given was it is actually you have to use L model, and then you have to follow up with the Elmore delay formula. So in that case your calculation becomes extremely simple. Okay, now we move to the second question. Again, it is a similar of the previous stage, but the question here is you have to apply a Elmore delay, but in the pi model. In the previous case, it was L model. Here, it's a pi model, and there is not much difference between L and pi model. Okay, so we will make that. The question given over here that R is equal to twice X and C is equal to 3Y, and it has been divided into 4 segments. In the previous case, right, individual resistance and capacitance was given, that R L by N and C L by N. In this case that is not given, so what we will do, we will calculate the individual resistance and capacitance, and this will be twice X, right? So this is my capital R, or let me remove this. Okay, so this small r of the individual component will be R by 4. Okay, this will be twice X by 4, and this will be X by 2. So this you have to note it down. Then the second thing is small c. This will be capital C by 4. Okay, then this will be 3y by 4. Okay, now what we have to do, we have to divide this entire interconnect into 4 segments, but you have to follow the pi model. Okay, so when we talk about pi model is like this. Okay, so there are actually 4 resistance component in which it is divided, right? So that is similar to your L model. However, when we see the number of capacitance, it is actually 5. Okay, so every capacitance is grounded. Okay, and individual component of the resistance is X by 2, so that we can easily see X by 2. Okay, in all the internal capacitances, you can directly write 3y by 4. Okay, 3y by 4 and 3y by 4. Now the question is how much capacitance you are left with. So you are left with 3y by 4 capacitance. You have to distribute this 3y by 4 capacitance into 2 capacitor, right? So you will equally divide, and you will write 3y by 8 over here and 3y by 8 over here. Okay, so this is how you will make the pi model. Now once this model is there, you just apply the Elmore delay formula. Okay, so once we apply this Elmore delay formula, uh, so this x by 2 will be actually multiplied by this 3y by 4. Okay, so I will write delay is equal to this x by 2 multiplied by 3y by 4. Okay, then we have x. So x by 2 plus x by 2, that is x, that is also multiplied by 3y by 4, x multiplied by 3y by 4. Then we will have x by 2 plus x by 2 plus x by 2. We will have 3x by 2 multiplied by 3y by 4. Okay. Then how much x we have? 2x. Okay. So 2x will be multiplied by 3y by 8. Okay, so x by 2 multiplied by 3y by 4, x into 3y by 4, 3x by 2 multiplied by 3y by 4, then 2x multiplied by 3y by 8. Okay, so let me see if this is in the equation. I think, yeah, this is the last one. Okay, so this is how you calculate this particular question. Now, moving to the third part. So, in the third part, let me read for you. A 10x unit size inverter drives a 2x unit size inverter at the end of 5 wire. Okay. 4 lambda wide metal 2 wire in a zero point 0.6 micrometer process. The wire width is 1.2 micrometer. The thickness is 0.144 micrometer. Then the wire has a seat resistance of 0.08 ohm per square. The capacitance is of 0.2 femtofarad per micrometer. Construct a pi model for the wire, and please note that it's a pi model. Okay, so the gate capacitance is 2 femtofarad per micrometer. Again, it is in micrometer. Effective resistance is 2.5 multiplied by micrometer, right, for NMOS transistor. Estimate the propagation delay using Elmore delay model and neglect any diffusion capacitance. And the lambda given over here is lambda equal to 90 nanometer, right? So much information. Let me break down it for you. So the very first thing which you have to write down is the wire width. Okay, so the wire width is 1.2 micrometer. Okay, so the wire is actually, so if you have the width, right, so you can calculate number of squares in the length. Okay, so what you have to calculate? Number of squares in the length. So this will be 500 micrometer. Okay, this is my 5 millimeter wire divided by 1.2 micrometer. Okay, so if we calculate this, this will come 4167 squares, okay, in length. So there are 4167 squares in length, right? So why I have calculated that? Because we have been given with the seat resistance that is 0.08 per square, right? So we can multiply with the number of square and we can get the total resistance. So the total resistance, we will calculate total resistance is equal to 0.08 ohm per square. Okay, so let me, and then 4167 square. Okay, so if you multiply this, you will get 333. Okay, so this is your resistance, 333 ohm. Now what you have to do is you have to calculate a total cap, because your delay is dependent on both resistance and capacitance. So total cap will be, so here the gate capacitance given as 2 femtofarad per micrometer, but the capacitance of the wire has been given as 0.2 femtofarad per micrometer. And what is the length, or sorry, what is the width of the wire? This is 5000 micrometer. Okay, so because it has been normalized by width, so once you do that, the result will be actually 1 picofarad. Okay, so please note that here we have not divided by the number of squares, because the resistance was given in squares, right? So that's the reason we have to multiply by the square. Here we do not have to in the capacitance. Okay, now once you have the resistance and capacitance, right, the question says that this is 4 lambda wide metal tube. Okay, so this unit inverter has if it has a 4 lambda of wide NMOS transistor, then 4 lambda W of 4 lambda will be 4 multiplied by 90 nanometer. Okay, so 4 multiplied by 90 nanometer will be 0.36 micrometer. Then we have this is for NMOS. Okay, so if we consider the mobility ratio, then we have to multiply it by 2 times for the PMOS because it's an inverter. Okay, for beta equal to 1. Then Wn is this, Wp will be 8 lambda, and here it will be 0.72 micrometer for PMOS. Okay, so 0.36 plus 0.72, so this is our width of both NMOS and PMOS. So your unit inverter actually has an effective resistance of, if we calculate the effective resistance of unit inverter, right, the question it is given that R is equal to 2.5 kilo ohm per micrometer, sorry, 2.5 kilo ohm micrometer. So so effective resistance will be 2.5 kilo ohm micrometer. So that's the width, and this is given for the NMOS, so you have to divide by the width of the NMOS. This is equal to 0.36 micrometer, so you will get the actual resistance, and actual resistance will come out as 6.9 kilo ohm. So now you have the actual resistance, so effective resistance also. Uh, so once you have that, what you have to do, you have to find out the gate cap. Okay, so gate capacitance. Okay, so gate capacitance will be 0.36 micrometer of NMOS plus 0.72 micrometer of PMOS. Okay, multiplied by the capacitance that has been given is 2 femtofarad per micrometer. So 2 femtofarad per micrometer, right? So this will be around 2.2 femtofarad. Okay, micrometer and micrometer will get cancelled. So once we calculate all of this, you just have to apply Elmore delay formula, right? And please note that it's a pi model. So when we consider the capacitance, it will be C by 2 instead of C, right? So here it is 1 picofarad, it will be 500 femtofarad, right? So I'm erasing this part uh, till now. And once you directly apply the formula, right? So the formula I'm directly applying. So the equation will be like, okay, so 690, right, because 6900 ohm was your uh, mm, was your effective resistance, and it is actually multiplied, if you can see, it is 10 times of unit size, right? So if you calculate for the unit size, it will be 690, or if it is multiplied by 10 times, the resistance will go down by 690. It is multiplied by 500, right? So that's my cap, right? So 1 picofarad divided by 2, then it will be plus 690 plus 330. Okay, so that's the resistance which we have calculated earlier, and then it will be actually multiplied by the total capacitance. So if you see the total capacitance over here, this will come around, so this is 500 femto, okay, 500 femtofarad plus 500 femtofarad plus 4.4 femtofarad. Okay, and once you calculate this, you will get 0.86 nanosecond. Okay, 0.86 nanosecond, this is the right answer. So this is question number 3. Okay, now moving to question number 4. Here we have 3 bars, 1, 2 and 3, and these are 3 interconnects, A, B and C, and please note that these are in same plane. Okay, and they are parallel to their neighbor, and as shown in the figure you can see here, each wire is of 1 millimeter and has a capacitance of 0.08 femtofarad per micrometer. Okay, so this is the capacitance of the uh, of each of this wire to the ground, and 0.12 femtofarad micrometer to its neighbor, right? So adjacent capacitance is 0.12 and the capacitance to the ground is 0.08 femtofarad. So these are the two things which has been given to us. Now each line is driven by an inverter with a 1 kilo ohm effective resistance. Okay, so that is also given. Right now estimate the contamination and propagation delay of the B wire and neglect the parasitic capacitance and resistance. Right, so the contamination delay means what is the fastest delay of this three interconnects, right, when something is flowing through these three interconnects, and the propagation is the worst case delay. Right, so question it has been given that the C ground is 0.08 femtofarad per micrometer, right? And yeah, and you can see each of the wire is 1 millimeter, so we can multiply this with 100,000 micrometer and you will get uh, the capacitance as 80 femtofarad. Okay, now when you are talking about best case, right, we assume that all the these three are actually the are switching in the same direction. Okay, when all of these three are switching in the same direction, what will happen? The C effective will be nothing but C ground itself. Okay, so this will be R multiplied by C. R is 1K multiplied by 80 femtofarad. Okay, this will be 80 picosecond. Right, it's very simple. So that is the first part. This is my the TCD, contamination delay, and I have 1, 2, 3, 4 answers. Sorry, 5 answers with 80 picosecond. Now moving to the worst case, the propagation delay. So when we calculate the TPD. Okay, so this is TCD. Now we calculate the T propagation delay. So T propagation delay will be when we will do is will be C ground, okay, plus 2 times of C adjacent, right? C adjacent, right? Plus again 2 times of C adjacent. Okay, so this will be your propagation delay. And C adjacent is how much? You can see 0.12 femtofarad per micrometer. So C adjacent will be 0.12 femtofarad per micrometer multiplied by 1000, right, micrometer. This will be 120 femtofarad. Okay, so this the final result will come as 80 plus 120 into 2 twice 240 plus 240, and this will come as 240 plus 240 480 plus 80 560 picosecond. Okay, so you can see 80 picosecond and 560 picosecond. So this is the correct answer, right? So this is how you calculate the contamination delay and the propagation delay of any interconnect, right? So you have to consider that, okay, which are the cases when it will be fast and which are the cases when it is slow and what condition you have to follow there. Okay, moving to next question. So next question is there are options. Which options are always true for adding repeaters in a interconnect? Okay, so this we have to actually find out, and there are many options. So let me directly give you the answer that if you have multiple repeaters mean you are adding buffers. Okay, you are adding buffers. If you have multiple buffers, your delay is going to increase, right, because each of the buffer will add some delay. Okay, so that's the first point. Now the second point is the faulted technology repeater have lower parasitic capacitance as compared to conventional inverter repeater, right? So this faulted technology repeater are specially designed to have lesser delay. So that's the second point, and it's specially designed to have lower parasitic cap as compared to conventional repeaters, right? And the third point is the minimum delay per unit length does not depend on the number of repeaters. Okay, because you are dividing the delay per unit length, right? And whenever you have normalized it, right, it doesn't matter how much your the entire delay is, right? So per unit delay will remain the same. Okay, rest all the arguments are not correct. Okay, so these three arguments are correct. Now, moving to another question, that compute the delay per mm of a repeated wire in a 65 nanometer process with VDD is equal to 1 volt. Okay, assume the wire on a middle routing and it has twice x of the width, spacing and height. So its resistance is 250 ohm millimeter. The capacitance is 0.246 picofarad per millimeter. The FO4 inverter delay is 22 picosecond. Okay, so many informations are given, right? And how we have to just find out the energy per bit. For finding the energy per bit, uh, what you have to do is you have to first find out, okay, what will be your TPD. Okay, and because in the question it has been asked that first you find out the delay per millimeter and then you have to find out the energy per bit per millimeter. Okay, and uh, this has been actually discussed in the class, and I will just directly write a formula for the TPD, right? So there is a derivation corresponding to this. This is actually 1.67. Okay, then it is actually multiplied by FO4 delay. Okay, then it is multiplied by R, then multiplied by C. Okay, so this will be 1.67 and root, what is the FO4 delay over here is 22 picosecond multiplied by 250 multiplied by 0.246 picofarad per millimeter. So the final answer will be 61.42, okay, picosecond per millimeter. So this is the propagation delay you get. Then 4 to 8 it will be. Then what you have to do, you have to calculate the energy, right? And you have to divide it by L. So when you calculate the energy divided by L over here, this equation will actually come like 1.866 CVDD square. Okay, CVDD square. And if you put the value, you will get 0.459 picojoule per millimeter. Okay, so VDD given is 1 volt, right? Capacitance is already mentioned 0.246, right? And if you multiply that, you will get this answer, right? So the final answer is this one, right? 61.428 picosecond per millimeter and 0.459 picojoule per millimeter. Okay, now moving to another question where this is actually of week 9. As of now, what we were discussing was of week 8, right? And this is a very easy question in that regards. Here, the question has been asked that a chip is composed of random logic, has an average activity factor of 0.1, right? So the alpha given is 0.1. You are using a standard cell process with an average switching capacitance of 450 picofarad per millimeter square. Okay, so C average given is 450 picofarad per millimeter square. Okay, estimate the dynamic power consumption if your chip has an area of 70 millimeter square. So the area has been given, so I can calculate the C. Okay, so C will be 450 picofarad multiplied by 70. Okay, so this will be my C. Then it runs at the frequency of 450 megahertz. So the F is 450 into 10 to the power 6. VDD is 0.9 over here, right? And if you know directly the formula, you can directly write alpha C VDD square F, right? So this is the formula of the dynamic power, P dynamic. Okay, and if you calculate this, so this will be 0.1 multiplied by 450. Okay, so 450 megahertz. Okay, then right, so 450 megahertz. Okay, so first you have to multiply it by 450 megahertz. This is alpha into frequency alpha and F. Then you have to multiply it by C also. So C is 450 into 70 into 10 to the power minus 12, right? So this is your C. This will be multiplied by your VDD square, so 0.9 square, and the final result you will get is 1.148 watt. Okay, so this the answer will be 1.148 watt over here. So yeah, this is the question on dynamic power. Okay, you have to understand that dynamic power is mostly in most of the cases, the dynamic power is the major chunk of power consumption, and it happens whenever there is a switching. Okay, so whenever the input or the output or the internal node switches, we call that is dynamic power. Whenever the current flows, right, and the power consumption happen due to switching of internal node or output or input node, right, that is considered as a dynamic power. When there is no switching that is happening, the output is idle, the input is idle, and the internal nodes are also idle, that power, whenever it is leaking, it is called as leakage power. Okay, so you have to actually distinguish between the two, and this is the formula we have calculated for the dynamic power. Now the last question over here is, okay, what will be the switching probability of y, output y, in a 3-input NAND gate? And the 3-input NAND gate has been given over here, right? Let me just quickly draw the truth table for you. A, B, C, this is y, right? So if it is AND gate, it will be all 0 and last one 1, and if it is NAND gate, all 1 and the last one is 0. Okay, so for NAND gate, it is actually what it is, right? So this is PA multiplied by PB multiplied by PC. Okay, and this will be 1 minus PA multiplied by PB multiplied by PC, right? So this will be the switching probability of that, right? We do not have any option of 1 multiplied by PA dot PB dot PC, right? So let me break this PA PB PC using De Morgan's law. And if you have two bars over here, this will be 1 minus PA bar plus PB bar plus PC bar, right, to the whole bar, and this will be your correct answer. Okay, so in this lecture we had only 8 questions, um, uh, and we had a great discussion in the last class, right? And this is for to be uploaded in the YouTube. Still, if you have any question, anything in this particular aspects, right, feel free to post into the discussion forum or in the WhatsApp group, or you can mail me, right? Please make sure that you understand the concepts very clearly. Okay, so that's our goal. For all of this session, the goal is that you should understand the concepts clearly. Okay, so thank you everyone. So I will stop the recording.